Okay, welcome class to the second lecture on multibody dynamics. The topic for today is a systematic approach. Oh yeah. I can do this. I can do. No, don't worry. Oh, like this. This is even better. Yeah. The topic of today is systematic approach. Let me check if all systems are running. Yeah. Chapter 12 in the book. Before we start, I'd like to do a short question on if everybody is happy with the homework and the peer grade system, and do they have remarks, questions or things, pressing remarks, pressing questions on the review and homework system. Yeah, I see one hand. That's a review. Okay, the answer is the question is somebody got a review and the thing which was clicked and the comment didn't disagree, and I think that the clicked thing is wrong. Well, as a one who is reviewed, you have the opportunity to react to that. So just write reviewer 1, 2 or 3, whatever who it was, and the sub question. You made a mistake there. Just write prose out there. That's no problem. It will inflict, of course, your grade, and you will feel, of course, not so happy if he did the wrong thing. But if 3 randomly chosen reviewers did the same wrong thing, then you're really in trouble. But the thing is that the thing sort of levels out these problems. That's the whole idea. Does it answer your question? Yeah. Other questions? Yeah, I see another hand. The question is if it is possible for the homework assignments to be earlier available, and the answer is no. And I can explain why. Because the night before, until 2:30 in the night, I'm busy with it. Really, my schedule is so full. I have to press it somewhere, and my life is full of good promises, and it's always to do things in advance, but it's like the tax return form. Always at the last moment I'm fixing this, so sorry. In my next life I will do a better job. Other questions? Okay, let's kick off. And of course, we start our lecture with Kahoot. Okay. By the way, I looked into other systems. I also looked into the system which is available in Brightspace, the quiz system. Doesn't work for this class, period. I investigated it, it won't work. It's not it's self-paced, and that doesn't work for the class. So. Okay, so we stick to Kahoot. Yeah, I have to reformat a little bit. Bookmark, yeah, this should work. Classic. Yep. You can add a name to your number. I only look at the number, and then when you're in the Hall of Fame, then it says class. If you are class. Oh, for the record, there's again a high turnout here in the room. Yeah. This looks about the number of last week approximately, yeah? Are you ready? I do have a Greek PhD in my group. He's Greek, yeah, but it doesn't help. Huh? Sorry, there was some glitch in the system. Yeah, I think almost everybody answered. Oh, okay. And it's also correct. I don't know what went on. Okay. That's not my student ID. Okay. Don't touch anything. Yeah, this is in follow-up of last week actually, but please read closely. Yeah?
Could you click on the image?
Yeah, but it will not become larger. No. Oh, this one, yeah, sorry, yeah, I can do that. Yeah, but, well, let's see. Lifestream. Yeah, very good. BVR in the room? This hashtag is number of, number of rigid bodies, number of revolute joints, number of degrees of freedom. So we have a mechanism which consists of rigid bars and pin joints, and you just have to do a little bit of counting. Or use your intuition. Okay, Lifestream. Yeah. Okay. So I will repeat the correct answer. There was like 6 bodies, 6 bodies, 8 joints, 2 degrees of freedom, right? Let's start with the 6 bodies. Well, it was everywhere 6 bodies, so that was not an issue. Then how many joints are there? And let's just do simple counting. This is it. This bar is joined to the ground, that's 1. This bar is joined to this one, that's 2. This one to this one, 3. This one to this one, 4. This one to this one, 5. This one to this one, 6. This one to this one, 7. This one to this one, 8. Now, a lot of you have 7. Why? Well, I only see 1, 2, 3, 4, 5, 6, 7 circles, so it must be 7 joints. Well, you totally forget the definition of a joint. 2 members being in one joint. And this is like a triple joint thing or something like that. Anyway. Now, how do we get the number of degrees of freedom? Well, you see it when you know it. You know it when you see it. We're not going to do that. We're not going to do you know it when you see it. It's not pornography, it's mechanics. So, how do we calculate that? Well, if you know the type of bodies and if you know the type of constraints, it's just a formula. If we have 6 bodies, then 6 times 3, that's as a free body. And then if you have a joint, a revolute joint, it's -2, so it's 2 times 8. And then if you do the math, then the outcome of that math is +2. That's 2 degrees of freedom. Okie dokie. Next. BVR. It fell down. So this is about speeds. So we have in some configuration this mechanism, rigid bodies with constraints. There is some angular velocity given. And then the question is, for this initial angular velocity, what are actually all the initial speeds and angular velocities of all the bodies? Yeah, and please discuss with your neighbor. Yeah, pretty good. Okay, nothing to talk about. Last question. Okay, Lifestream, but you almost answered, yeah. Perfect. And why do we have two correct answers? Well, it all depends on how you defined your forces. Yeah, you're free. When you draw the free body diagram, you can say, oh, that force is in that direction or it's in that direction. And independent of from those free body diagrams, you derive your constraint equations. And that you could also put a minus sign in front of that. Or you can multiply it with pi or divide it by e, or you can all kind of things. So in principle, I mean, there is a sign and a constant factor thing between the two. But the gist is that it's the transpose of the other one. Very good, very nice, very nice. What do we do now? Now we have to save everything. BVR. Da-da-da. Come on, guys. Oh. Get feedback, yeah. Save the results. Direct downloads. Save to a drive. Save. Okay, that is done. Now we go to okay, so after the Kahoot, the first thing actually I want to do is to have a look at the results from homework 1. So let's look at the results of homework 1. And what did we calculate? So the problem was this double pendulum thing, right? So we had these two on top of each other. This was the initial condition, I think, in the first question. Everything was upright. Then we had body 1 here, and this is body 2. There was a loading of just gravity, and it was in the x direction. So this was m1g, and this was m2g. And then the big question, Heike, don't get mad. Coordinate system. Yeah. Okay, and an origin maybe, well, whatever. And then if we look at our work, we calculated from this the all the accelerations of all the bodies, and together with the constraint forces. So if we look at the acceleration, what did we calculate? X double dot 1, y double dot 1, phi double dot 1, x double dot 2, y double dot 2, and phi double dot 2. And my results, and I mean there can be errors in it, but it was like this: 6.29 meters per second squared. This was 0. Okay. This was minus 20.99 radians per second squared. This was 10.51. And this was 0. And this was 6.98. Yeah. And then all the forces, the constraint forces was like this. HB and VB. Minus 1.99, 0, 0.490, and everything is in newtons here. Okay, now it's all very nice that you have these numbers, and but the big question is, of course, is it correct? Now you can, of course, check with your neighbor, do you have identical research, but making identical errors is also possible, so that's not a close case. So what do you do? Well, if I look at these numbers, the first thing which attracts my mind is the zeros. I mean, I see zeros here. I see zeros in the y direction. So the question is, could that be correct? Why is there no acceleration in the y direction? Yeah, please. Yeah, it's a rigid body, and there's a constraint in the y direction, but still then there can be an acceleration in the y direction. If there's a circular motion, I mean, then you can have a centrifugal acceleration. Is there a circular motion? Is there an angular speed? No. So there are no, it's constrained in the vertical direction. Then it still can rotate, but there is no initial angular velocity. Ergo, there are still no centrifugal accelerations, and therefore I believe it's like a religion. I believe that they should be zero. The math tells me they are zero, but my belief is that. Okay. Next, what do we see? I see a very large negative number here. Is the sign correct? Minus 20. Yeah, because plus is in that direction, and I expect that everything will fall into that direction. So that's okay. Well, don't look at my hand motions because it's mirrored. Yeah. Whereas if I look in the mirror, I see myself, but it's not me. Yeah. Okay. And it's super crazy, like on the phone, to see yourself mirrored, right? Mirrored, or whatever. This gets too complicated. Forget it. We're going to do mechanics. A large number, 21 radians per second squared. Do you have any feeling for what that means? Should it be 2 or 200? Frankly, I have no idea at the moment. Yeah, so let's skip that. Everything you don't know, you just skip. That's how it works in life. Well, that's life. Let's look at other numbers. So, for instance, the linear accelerations. So for body 1, this is also super confusing. I write this from top to bottom, but here it's from bottom to top. Yeah, you can make 1,000 errors. Okay, so this is body 1, this body, and this is the linear acceleration here. Now, if it was only that body and there was nothing else in the universe but that body and gravity, then it would just fall with gravity, right? So, and if I look at the number, it's less than the acceleration of gravity. And I sort of expect that because this body is connected to the ground and this body is connected to another body, so he has to service other things. He cannot be by his own in that gravity field. So, but maybe the other things are holding it back. Like a hinge to the ground is holding it back. Another body connected is holding it back to fall with that acceleration. So, seems okay. But now we go to the second body, and that is this body. And I must have made an error there, because now suddenly body 2 is falling with an acceleration which is larger than gravity. I should immediately put a patent on that, right? How can things in a gravitational field fall faster than gravity? The answer from the audience is if they get pushed. And that is the absolutely correct answer. Who is pushing body 2? It must be that body 1 is pushing body 2. Can we check it? How do we check that? Yeah, let's look at the constraint forces. So then we look, and now we have to look at our definition, but if I remember well, and my remember is here on paper, this was body 2, and I think this was the definition of HB. So, and this was body 1, and this is also HB. And then HA was like this. Yeah, I should say this is body 1 and this is body 2. So with this sign convention, yeah, clearly body 1 is pushing body 2. Okay. So it all begins to fall into place, right? Remains the question is, how can body 1 in a gravitational field push body 2? How does he do that? I mean, they all fall in a gravitational field. How does he do it? Yeah, because body 1 is not falling like a straight body down, but it's hindered, it's restricted in its motion by that joint at the origin. And maybe the acceleration of that point here is larger than the acceleration of gravity. So now we can check that if we just look at it as a free body. So if we just say, okay, well, let's assume we only have this free body 1. So we cut everything loose, and then we want to know, what is this acceleration here at this endpoint if it's falling within a gravitational field? Like this. And if that is larger than the acceleration of gravity for this free falling a pendulum thing, then I would say, yeah, it sort of all fits because it pushes then the other body. Okay, what is that acceleration for such a free falling pendulum? One G, 2G, 0.5 G. Sorry? 1? Why? Yeah, and you believe it's 1G. Now let me tell you, this multibody dynamics is not a religion. It's not about belief. It's about knowledge, about knowing. I know it. So do you know it is 1G?
If it's one body, yeah, but it's multiple.
Okay, then you know. How do you know? Sorry?
I guess we don't.
Okay. The answer is, I guess we don't. So how can we discover what that acceleration should be? Do we have math for that, or rules, or laws, or is there a way to find it out? Measure it. Yeah. Okay. Good luck. The question is, isn't it caused by the attraction force between the beam and the Earth? I don't understand. Yeah, I don't understand the answer directly, but I want to stay first of all by that are we using religion to find out what A is, or are we just doing math? You should be doing math. Okay, so I'm happy with that. Then you could write the Newton-Euler equations for this body, or do a free body diagram, but I remember from Heike's course, Advanced Dynamics, that this is a rotation about a fixed point. And then, for rotation about a fixed point, I can apply Euler's law. I can write, oh, the sum of the torques about point A is the mass moment of inertia about A times the angular acceleration, if this is the angular acceleration. That's just Euler's law, where I not use the center of mass point as in a general sense, but a fixed point. And for a fixed point, this holds. If point A is accelerating, that doesn't hold, but if it's a fixed point, it holds. Okay, well, then the only thing we have to know is the sum of the applied torques. This was a length of L, right? So the sum of the applied torques in this case is mg L over 2. And the mass moment of inertia at A, oh, I don't know. I only know the one at Cm. So the one at C is 1 over 12 ml squared, right? That everybody knows. Everybody knows, yes. Now, how do you get from C to A? And that is by the parallel axis theorem for those English-speaking ones. For the German ones, it's the Steiner rule. And for the Dutch guys, it's the Regel van Steiner. Yeah. So what do we say? At A, it's the one at the CM plus the mass times the distance squared. So in our case, that's 1 over 12 ml squared plus 1/2 L squared times m. And then finally, 1 over 3 ml squared. That is the answer. Okay, so that is here 1 over 3 ml squared phi double dot, ergo the acceleration of the body, angular acceleration is 3 over 2 g over L. And I'm happy with the units, because it's Newton per, it is meter per second squared divided by meter, so per second squared. And a unit and a radian is apparently the same, which honestly I still don't understand. But they say so. Radians and non-radians are the same. Anyway, so per second squared, so that's okay. Now what is the acceleration of that point? Well, the acceleration is of course the distance times the angular acceleration, so that's L times phi double dot. So I come to 3 over 2g. And yes, that is larger than the acceleration of gravity. So we now have proven that the point is going with an acceleration of 3 over 2g. So it's falling faster in that gravitational field than a free body would fall. So it makes sense that body 1 is pushing body 2. Now how many time did we spend on this? 10 minutes? So well, yeah, it's good that you show a smile, because we spent 10 minutes on one result to see if it's correct and does it comply with our, well, not with our beliefs, but with our other knowledge, and do we find that it's a reasonable answer. And actually I expect you to do like this with your homework. I mean, of course you talk to your colleagues, and of course you use the studiespunt, snel, NL and whatever. But to be really that sure, check yourself. I mean, you know, most of it you know yourself. Okay, so that having said, it's all very nice. We now calculated in this configuration the accelerations by which the thing will start moving is maybe a wrong thing to say, by which the velocities will change in the spirit of Newton. Given the accelerations, we only know that the velocities will change with these amounts. But actually what we want to know, I mean it's all very nice, we want to know this. I want to know how the thing is falling. I want to know all the positions of the center of mass and the angle, the orientation of the body as a function of time. So how can we find this? How do we find the positions and the orientations of the bodies as a function of time? Yeah, I see a hand. Numerical integrate. Why not analytical integration? We have the equations. I see another hand. It's a good answer, but yeah.
Because it's non-linear.
Yeah, the answer is because it's nonlinear. You would think, oh, then we solve it by integration. I mean, we know all our integrals. The integral of x is half x squared, and the integral of cosine x is sine x. Yeah, and the integral of tangent. Oh, we don't have any tangents. We have sine and cosine. Of cosine, the integral of cosine is minus sine. Well, I know my package of integrals, so why not integrate it? But then you have to solve these equations, and you will find that if you will write the accelerations as a function of all the variables, you get a thing which we call wallpaper. It's a long formulas, and if you then put that into solve, then the computer crunches, and the ventilator, now that's the fan, is going to start to run, and you hear and you still have no answer, and you wait and you hear and your battery is going down, and so it doesn't work. So we have to stick to, in the case of these nonlinear equations, to numerical integration. So that is our trick, numerical integration. Okay, how does that go, numerical integration? So by that we can solve it. How do we do it? You had an idea, yeah?
Yeah, so we know the initial velocities and positions.
Yeah, so we know the position, yeah, at 0, and we know the velocities at 0, and then?
And then we can use the numerical time stepping, numerical derivation, numerical integration.
Yeah, okay, so I want to have the new position, x1 equals x0, and then plus, what do I have to write down?
Delta t times xo delta.
Yeah, and this one for now, with the speeds we will see. That's maybe that's the same. Yeah, I like this. I like this answer. So you say, well, the new position is the old position plus a time increment times the speed. Now, where does this come from? What is the origin of this? Oh, pen back. Origin. Why does this work? Where did you get that idea?
We also take acceleration.
Yeah, okay. I'm okay with that. Plus, what do you want to add?
Half times the delta t times x
Plus a half delta t. Kwadraat. Something like that? Yeah, could be. But for now, I'm just putting it in brackets. We could do it. I mean, even higher ones, right? If we have them. Third order derivatives, fourth order derivatives, whatever.
We are using like payload.
Yeah, I will get to that. But first, let's focus on this one. Where does this come from? What is the basic idea about this? Yes, it's a good answer. Our Greek philosopher. A Greek philosopher in order said, it's from the definition of velocity. It's actually Newton himself who came with that. Because how is speed defined? And let's forget about vectors now. So speed is defined as the limit case of some step, delta t going to 0, of what? Well, of xt plus delta t minus the x at t, and then you divide everything by delta t. That is the definition, by definition. And you already see, if you cook up this formula, if you just shuffle around some stuff, then you can write, oh, lo and behold, xt plus delta t equals xt plus delta t times x dot. Now, I omitted one thing, and that is the limit case. So this holds, and yeah, this holds for very small t. So I should make a remark like delta t should be very small, because I threw away that whole limit thing. And actually, if you don't want to throw that away, that limit thing, and you can add terms if you want to, and that is what we call Taylor or Maclaurin expansion. Okay, but this basic formula, this also for this numerical integration scheme, we also have a name. For the numerical schemes, there are different Runge-Kutta and Hoyne and all those kind of things. What is the name which goes by this scheme? And remember last week what I said. Euler, yeah. There he is. Every week we're going to talk about Euler. Yeah? So this is what they call an Euler step. And the interesting thing is, of course, that why is it not called a Newton step? Because it comes from the definition of speed, which was Newton made, or a Leibniz step, or something like that. And the reason is, of course, that these guys, these old geezers like Newton and Leibniz, they didn't do any numerical analysis. I mean, it was all very theoretical basis. They didn't go into these deep numbers. They didn't have to do roll dynamics of a ship and those kind of things, those practical things. Whereas the first who did really practical analysis with those Newtonian equations was, of course, Euler. And Euler was stuck with the problem of orientation, as we discussed last week. This week, Euler was stuck with, he ended up with equations he couldn't solve analytically. So we had to find a numerical way, and he just took the definition and came up with this idea. Okay, now let's do that in our problem. So in our case we have two things. We have positions, so the new position is the old position plus delta t times the speed at that position. And I think, why don't we just copy this, and I'm really going to copy it to show that it's really a copy. So copy, and then we just add a dot. Oh, go back. Then dot, dot, dot. So now it also works for the speeds. Yeah. So let's apply this to our problem. So then we have to write down the coordinates, x1, y1, phi1, x2, y2, phi2. And then we write them down at t is 0. And that is 0. The length was 0.6, so that's 0.3. This is pi over 2. That's a difficult number. Approximate, we're doing approximations. x2 is 0 again. This is 0.9. Yeah. And this is same pi over 2. Okay, and then the next step we want to make is let's take, for a time step which is rather large, 0.1. But I do that because we work in a decimal system, and then with the 0.1 it's easy. I shift. Multiplying with dot 1 is just shifting commas. I could take 0.105 through 6709, but I cannot do that. But the state is not only defined by the position, also by the speed. So we have to know what is the current speed. So x dot 1, y dot 1, phi dot 1, x dot 2, y dot 2, phi dot 2. Okay, what are they in the initial? T is 0. The initial speeds for the first assignment was 0, right? Everything 0. There were no speeds. Yeah. Okay, so then the new position, let's read our formula. The new position is the old position plus delta t times the speed. Okay, well, this is the speed, so I have to multiply this with 0.1. Well, that's not so hard. And then I add it up to this one. Well, that's not so hard either, right? I have a feeling that something is wrong. But I mean, it's just homework, so just continue. Just do what you have to do. Don't use your brain. Okay, that's the new position. Actually, I'm not so happy with it. The thing is not moving, right? It's a bit dissatisfying. Why is the thing not moving? No, but this is, in principle, this is okie dokie. I took it from the formula, the definition of speed, so why should I do that? Okay, if your car has 0 speed, and you want to know in 1 second where you are, do you know where you are then? Yeah. You stay where you are, right? It's in the definition. I mean, if you're not moving, then the coordinates don't change. Let's take a coffee break because I don't know.